um, on the dynamics of nanodust in the near-lunar space environment. I'll give you a 2-minute warning before questions.
Great, thanks. Yep. Okay, so this is work following on from what Amanda Cook was talking about just a couple of talks ago. So we saw this nanodust environment, and so the challenge is to try and explain how it might have got there. So just to summarize, so a transient nanodust population was inferred from UVS observations when viewing anti-sunward from above the night side of the moon. And so this was a very serendipitous discovery. It's very unexpected. I was kind of really surprised by it, and it's been quite puzzling. And so the best example that Amanda discussed occurred several hours after the peak of the narrow but intense quadranted meteoroid stream. And so, our feeling is that that somehow played a role in generating this nanodust population. And so, like I said, the big questions is, what is the source of this nanodust, and how did it get there? And so I'm sort of going to run through some ideas that might sort of try and begin to answer those questions. Okay, so just a summary of those observations. So night side of the Earth, of the Moon, looking at anti-sunward, and so looking at the scattering from along these columns here. And so as the LADEE orbited from midnight around toward dusk, we saw a drop in the inferred concentration of this nanodust population. And it's just sort of a little sort of subplot from what Amanda showed. And so this is the UVS data. This is a model fit for assuming grain sizes between 80 and 100 nanometers. You can see it doesn't really do a great job of matching the spectrum. But when you look at the Rayleigh scatterers with dust radii below 20 nanometers, it seems to begin to do a pretty good job of fitting it. And so the tricky thing from that is the UVS nanodust column concentrations for this event were in excess of 10 to the 11 grains per meter squared. That's assuming a 30 nanometer grain. So that's a lot of dust grains. Okay, so what is the source of this nanodust? One obvious question is, could it be part of the impact generated ejector cloud? And so then if you take a look at the Krivov model, which the ejector cloud impact generated ejector cloud model, or maybe stick some numbers into that and see what you get. So this is a plot of the cumulative ejector mass distribution. I can put it to dust radii down here. And so this is the total number of dust grains greater than a certain size. And so on this axis, and this is a grain radii along the bottom. Okay, so here is the LDEX regime. So this is for dust grains above with radii greater than about 0.3 microns. And so this is kind of, been detected. This is what we know about. But this region here, this is unknown. So I've extrapolated this line, this power law distribution, to smaller dust grains. And so this is where our nanodust population sits here. And so you can see that you really rapidly increase the number of dust grains. So I should point out that with this nanodust, so most of the ejecta by number, if this is true, would be in the nanodust. But I should point out that it only represents a tiny, tiny fraction of the total ejector mass. So I'm not increasing the mass. I'm just taking the same mass that we think's there and just dividing up into smaller pieces. So it's just increasing the number, not increasing the mass. Okay, so then if you plug that into the Krivov model and sort of estimate some ejector concentrations as a function of altitude, so ejector concentration here and altitude along that axis. Okay, and so this gray line here is the LADEE altitude. So that's so we're looking sort of away from the moon. So we're looking at dust, this fraction of the dust. And so the black line here is the LDEX sort of measurement or model prediction based on LDEX numbers. And then here is the nanodust for this sporadic background. And the red line is an estimate, for the contribution that the quadrantids might play, especially around the radiant point there. And so these are the numbers we get. So then when you add up the column, which is what we're interested in when we're looking at UVS data, these are the numbers we get. So for LDEX, we get like 290 grains per meter squared, so pretty small. But then when you kind of look at the nanodust due to sporadics, you jump up like to 10 to the 6. So that's a huge increase, which is kind of what you'd expect from that power law plot I just showed. And so when you fold in the quadrantids, you can maybe get up to 10 to the 7. But we're trying to explain 10 to the 11 or greater. So this is we're orders of magnitude too low. And so the Kruger model assumes that all the dust grains, that the motion is dominated by gravity. Maybe something else might be playing a role if an ejector is the source of this nanodust. Okay, so then we address with how did it get there, and think about the forces acting on nanodust and how that might affect the trajectories. And so one candidate is radiation pressure on nanodust. And so we're looking at nanodust between sort of 1 nanometer and 100 nanometers here. And you see this is quite a complicated thing to calculate. You need to kind of know the solar spectrum and the scattering and absorption properties of the dust. And you can see that, so with the bigger grains in this distribution, you kind of still get fairly weak accelerations, and it drops off quite rapidly when you go to even smaller nanodust sizes. And so it's just kind of a fairly weak acceleration source. And we consider the solar minimum case and the solar flare case, and you see that when there's a solar flare, the smaller dust grains get a little bit of a boost from that. Okay, so then when you think about how this acceleration affects, how it compares with gravity, we've taken this ratio here of radiation pressure over lunar gravity as a function of altitude, and you can see that you have to kind of get out to sort of tens of lunar radii before the radiation pressure starts to dominate over gravity. So you have to be quite a ways from the moon for it to be important. So the next candidate is the Lorentz force acting on nanodust, and so the acceleration is a function of the charge on the grain, the mass of the grain, and the convection electric field and the B cross B, which is the velocity of the dust cross product with the IMF. Okay, so basically, the message from this is if you don't have any charge on the dust grain, you don't get any Lorentz force, and so you kind of need to get a handle on how the dust grain charges up. And so this is the timescale of dust charging here as a function of grain radii, and I've marked out here like the 1 hour mark. And basically, we'd expect that in sunlight, photoemission would dominate, and the grains would charge up to about 1.8 volts. And the charging time scales would be pretty long, so you're talking like tens of minutes, hours. And so we take from this the initial trajectories of the nanodust would depend on the charge they acquired during the injection process. And just another point here is that with these very tiny grains, you're actually counting the charge on the dust grain in electron charges and elementary charges, so that they're collecting very few net charges. Okay. So then when we look at the acceleration from this, so we've taken a test case of like a nanodust grain in equilibrium, and with this standard convection electric field for the solar wind, and so typical conditions. And so you find from this is that the E field term in that Lorentz force dominates near the moon. And this V cross B term you can pretty much ignore. And so this is kind of telling you that these dust grains are just sort of zipping along the electric field direction. So then when you do the same comparison to see how it compares with gravity, you find that that the Lorentz force can begin to exceed gravity sort of when you get to about a lunar radius away from the moon, when you're talking about the 20 nanometer grains that we think we're seeing. But even for the tiny stuff, I mean, that stuff's just exceeding gravity just at the surface, and that's just disappearing. Okay, so then the question is, how would these forces affect nanodust dynamics? And so, so I go back to the Kruger model and think about the speed distribution of the ejector. I've taken the cumulative distribution here. So this is saying that 100% of the grains all leaving the moon with at least this ejector velocity here, and this is impact ejector speed in meters per second. And then up here you get to the escape velocity here. And so this assumes the nanodust, is leaving the moon and it has the same speed distribution as the larger dust grains detected by LDEX. So then, when we consider like a 1D nanodust time of flight for illustration, so the reason I do this is because sort of dwell time for the dust in the exosphere is indicative of the contribution to the line of sight concentration. So kind of help sort of tie into to what UVS saw. And so what we see is that sort of about 0.2% of the ejected dust is getting to sort of 1,000 kilometers or so, and it's hanging around for timescales of hours. And so this immediately sort of suggests that the Lorentz force is going to be important. Okay. And so this plot down here is just sort of the time to the maximum altitude as a function of ejection speed. And as you see, you kind of asymptote towards the escape velocity here, shown in this line. And you can see you kind of go from minutes, hours, and to days. So this, these terrains can spend a long time above the moon. So the next thing to do is to sort of include the effects of the Lorentz force. And so I just, again, make some simple assumptions about the convection electric field and the charge and dust grain, and consider the 20 nanometer grain. And so then we consider the case where the Lorentz force is acting against gravity. And so basically it's so making it easier for the dust grains to escape. And so this is similar to the situation on the dawn side of the moon after the quadrantids. So when we do this, we've got this, so the answer here is this kind of red line here. And you can see what happens is that you actually, it actually reduces the effective escape velocity, which is kind of what you'd expect, by quite a bit. So it goes from sort of 2.4 kilometers per second down to 1.9. And so that gives you like about a factor of 2 increase in the escaping ejecta, just to give you an idea of how that affects the distribution. And so you'd expect this would act to increase the nanodust line of sight column concentrations, column abundances, because sort of, the dust is spending longer above the surface. So then if you consider the opposite case, where the Lorentz force would be acting against gravity, that's sort of similar to the situation you get on the dust side of the moon, sort of after the quadrantids. You find actually that if the U field stays constant long enough, that actually no nanodust can escape and everything's effectively trapped. It's this green line here, so nothing escapes. And so you can get time of flight reduced to sort of less than days, basically, for the very fastest particles. Okay, thanks. Okay, so then the simple argument here with this very simple model is that this could play a role in the post quadrantid midnight to dusk decrease in the UVS nanodust column concentration. So on one side of the moon, the dust is being sort of helped to escape, and on the other side, it's being sort of trapped. And so this could kind of give you a difference in the abundances that made the UVS saw. Okay, so again, this is the sketch that Amanda showed. And so, like I said, we had the convection electric field going from right to left during this interval, and so dust ejected from here would be sort of pushed out that way, and dust ejected from here would be kind of pushed that way by the Lorentz force, and this could kind of give you some sort of a asymmetric sort of distribution of nanodust around the moon if it was sourced by as part of the ejector population. And so this is our current kind of best guess for what we think was happening during that interval and how you might be able to get this nanodust. But making up that huge difference between the Cribble estimate and the measure in the inferred dust abundances we've still got a long way to go. So in summary, so the UVS observations of nanodust are pretty difficult to explain, and I think we need to sort of get a little bit more sophisticated with our modeling. So estimates from the Krivov impact ejector model applied using the LDEX parameters fall short by orders of magnitude. So there's obviously something more going on than is included in that model. So any nanodust in the near-lunar space would be slow to charge, so that suggests that the initial trajectories depend on the charge acquired during the ejection process. Radiation pressure has a minor effect until you get quite a ways from the moon. The Lorentz force seems to be the one that maybe is most significant, especially the U-field component. While you're still in the Hill sphere, where lunar gravity tends to dominate over Earth gravity, and especially it's especially important once you get to ejector speeds near the escape velocity. That's where this kind of really has an effect on the dynamics. So the Lorentz force could perhaps act to increase the line of sight abundances for nanodust and form asymmetries in the distribution of the nanodust around the moon. And yes, it could get rather complicated and be dependent on variations in the solar wind. Okay, thank you.
So my expectation is that nanodust grains created in a microplasma discharge from a micrometeorite impact would launch with a negative charge and initially go in the opposite direction. I wonder if you consider that.
Yeah, so one suggestion is that when you do get an impact plasma and you get dust thrown up, is that it tends to be the larger grains, because they charge faster, tend to gobble up all the electrons from that plasma cloud, and so they tend to come off. So they more likely come off negative. And so the tiny nanodust grains that take a very long time to acquire charge, would probably stay relatively neutral. And that's kind of why I was talking about, with the charging time scale discussion, I was kind of assuming that it started off neutral and had to acquire that potential, from photon emission.
Okay, thank you.
Yeah.
I'm sorry, I think we need to move on, so maybe you can ask your question afterward. Our next talk is by Mihai Harani,